Hey, good afternoon, everyone. So I'd like to welcome you guys all to the Chemistry Magic Show here at SFU, Simon Fraser University, Burnaby. And my name is William. We also have here James and Calvin as well. So let me just begin by acknowledging that we are privileged to gather here today on the unceded traditional territories of the Squamish, Tsleil-Waututh, Coquitlam, and Musqueam peoples. We thank them for having cared for these lands and waters since time out of mind and look forward to working with them in partnership as we continue to build this great city together. If you know whose territory you're currently on, please take a moment to reflect on this. And if you don't know whose land you're on, I encourage you to look it up and make yourself familiar with the indigenous peoples whose land you occupy.
Alrighty, so as you may know, Science Rendezvous is an annual Canadian national STEAM celebration that's staged all across the country, not just here. Now, the Faculty of Science at SFU is thrilled to stage this year's event virtually through these live chemistry demonstrations, all from the comfort of your own home. Now, this is your chance to connect with our science and outreach team, which is us, okay, along with some others, and learn more about the magic of chemistry.
All right, so we just wanted to highlight a few things that hopefully you'll enjoy this show that we'll be providing with you guys today. At the end of today, we'll also send you guys a survey to your emails that you signed up with, and hopefully you can give us some feedback about things you liked or things that we can improve on. On your video screens on Zoom, you can turn on live transcription if you have trouble hearing us, and that could hopefully give you a dialogue in terms of text to help you understand what we're trying to say. And of course, if you have any questions throughout this entire period, click on that Q&A box on the top corner, and you can send in some questions that we'll try to answer them as we go on. This show will be recorded, and at the end, we will be uploading this onto our website. And if you would like, you can watch this show all from the beginning again.
Okay, let's go ahead and get started then. So we have our lab coats on to keep us safe. We're gonna put on some gloves and some safety glasses as well. So safety is always the most important thing when we work with science and chemistry. So on here on this board, Calvin was nice enough to draw for all of us this beautiful drawing. I quite like it myself. Maybe I thought about just keeping it after today, but I don't know if you'll let me. But science is all about observations and describing what we see. So if we look at this sheet of paper, some of you guys may be confused as to, oh, I don't think I see a drawing or anything. And you know, I'm not sure, but let's try to describe and think about what we see. So what I see here is a rectangular sheet of paper. There's some texture on the paper. It might be a little difficult to see on the camera, but it does have some texture. And if we think about the color, we have this white sheet of paper. And so I'll tell you guys a secret. So Calvin did actually draw something on here, but right now you might not be able to see it. So maybe what we can do is perform some chemistry, do some reactions to make his drawing up here. So let's see what we can do. We have this white sheet of paper. Let's see what chemicals we have. We have some water from the tap. We have some vinegar, which is an acid. We have some soap, some detergents, and then we also have some, what is this? We have some Windex over here. So maybe some of you guys have used Windex at home. You usually use it to clean windows or anything else. It's pretty useful for that. So if we think about what color is Windex in and what does Windex look like? It looks like a blue liquid. And so if we think about maybe we can use our Windex to spray our drawing. So we have blue Windex plus a white sheet of paper. So I guess let's just take a look and see what happens. So I'm gonna spray a little bit on. Oh, what's that? Spray some more. Oh, we got a happy face. Looks like Calvin drew for us a sun. I quite like it myself. Let's see what else we have. What's over here? Ooh, we got ourselves a little umbrella. And then we got a beach ball. Well, I quite like the sound of this, the look of this. What else do we have here? Some sandcastles. Summer is just around the corner. So we've got sun, we've got sandcastles, an umbrella, and we have a beach ball. So I didn't expect that. So that is quite a nice drawing. I had to say so myself. So with that, is this magic or is this just science? So we have these blue Windex solutions. We spray it onto our white sheet of paper and we get this colorful drawing. We get some blue and we have some pink in there. So we can take a look at, why did that happen? How come when we sprayed it on, we get this colorful drawing? So Calvin over here has given me a flask of water. It's just straight from the tap, nothing special about it. So if we think about what does water look like? So water is a liquid, so it flows around. Water is clear or transparent because you can see through it just like the Windex. And water is also colorless because it doesn't have a color. Okay, so water, and then we also have a different chemical here. Something with a long, difficult name to pronounce. Maybe some of you guys at home can try and pronounce it on your own. Okay, did you guys get that? Might be really difficult to pronounce. Okay, so this chemical here is called phenolphthalein. Phenolphthalein. And so if we look at what does this chemical look like and make some observations, it looks like a liquid again, just like the water. It's clear, it's colorless, just like the water. So we can think about what will happen if we mix phenolphthalein with our water. So we have a poll, so you guys can take a look at or take a guess as to what color might we get. Will we get a colorless liquid? Are we gonna get something else like green, yellow, orange, red? What should we get? So we're mixing colorless with colorless. Okay, so let's take a look at what you guys guessed. Okay, so looks like we have a few options. Some people said green, some people said blue, some people said purple. And looks like those were the majorities. Okay, so let's take a look. So I'll pour out some of this phenolphthalein into our water here, and let's see who's right. Okay, just a little bit. Mix it up. And what do we get?
Looks like it's the same thing there, Calvin. Are you sure you added the right stuff?
Not sure. Maybe we can try adding something else.
Let's see. What about that Windex you had?
Windex? Yeah, I guess I could try adding a Windex, but I don't. What am I supposed to do with the Windex?
Well, I mean, we got a blue solution, colorless still, with some phenolphthalein that you had in there. So blue plus colorless, what is that supposed to make?
I imagine it makes blue, right?
Are you sure it's blue and not a lighter blue?
Well, I guess let's see.
All right. What do you guys think?
Yeah, maybe we can do a poll again, and then you guys can pick a color where you think it'll be. I think it'll be blue. Blue plus colorless should give us blue, right?
I think it should still be colorless.
Okay, let's take a look at what you guys think. Oh, we got some red, lots of blues, purple, black. Yeah, it looks like blue is the most common one. I feel like that makes the most sense. All right, let's see. So blue plus colorless. Spray some in. Oh, let's get some of that in there. What do we get? We get a pink liquid. I don't think that was what I learned in school, but okay. Okay, let's go with it.
But how do I get rid of that pink? What if I wanted to go back to colorless?
What can we do?
I know. Maybe we could just dump it out and just pour back water in there.
Oh, but I really like this liquid, so can we keep it?
Well, I guess. I mean, we can add something else. I mean, Windex is a type of base. Okay, so you may have heard of acid and bases before. So acids, where can we find some acids?
I think acids are usually pretty sour, right?
Yeah, they're pretty sour. I think if I remember the other day, I was having some fish and chips and someone was talking about acids. What was it? Oh, right. We had some vinegar. So vinegar is a type of acid.
Oh, I don't really like vinegar though.
Oh, I know. I
think
think we just had some pizza and with some soda. So inside soda, we also have some sort of acid. So I think we have some leftover soda cup here, so we can see. Okay, so we got Pepsi. So inside Pepsi, we also have something called phosphoric acid. Okay. We also have it inside our body as well. Right here in my tummy is what we call stomach acid. Okay, so we got some stomach acid. Now, I don't really have a lot of acids to provide right away, but I do have something to give off, and that is from my breathing. Okay, so here I have a straw. So what can I do with a straw? Well, I can either drink solutions out of it, like I would from my Pepsi, my soda, but we're not going to do that for chemicals. Okay, so we never ever eat or drink our chemicals that we have in our lab. Okay, instead, I am going to blow into it. So let me see if I can get this out here. I'm going to go ahead and blow into this. Now, what do we breathe out? So think very carefully. What do we breathe out? Is it oxygen? Is it carbon dioxide? Is it hydrogen? Is it nitrogen? What is it that we breathe out? Right? So if you're saying air, air is actually a mixture of different types of gases. And what we really breathe out is just carbon dioxide. Okay, not oxygen. That's what plants do, but carbon dioxide here. So watch very carefully as I go ahead and blow into this. So here we go.
All right, what's happening? We're getting a lot of bubbles.
Okay, this bubble comes from the detergent, right? So you get bubbles, but you can kind of see here. Here we go.
Oh, wait, what's happening? What's happening to the color?
I got magical powers, I think. Look at that. It's colorless again. Whoa, magic.
Oh, what if I want to get that pink color back again?
Well, I mean, we could probably try adding some more Windex in there.
Okay.
So let's see what happens when we add some more Windex here. Look at that, it's pink, right? Give it a quick swirl around, right? Notice that the color kind of stays pink. So that means we have a lot of base in there. But as you can see, it slowly goes back to colorless. Okay? And that's because I have a lot of carbon dioxide still. Yeah, I'm a good producer of carbon dioxide here. Now, carbon dioxide, when you mix with water, is called carbonic acid. Okay, so we're actually making some sort of acid here, so it slowly begins to disappear. Okay. Now, Windex is a pretty good base. okay? And we used phenolphthalein as an indicator to show us that, hey, when we have a base, it turns pink. Now, there's a lot of other indicators out there as well, okay? And one of them can be in a solid form rather than a liquid form. And this is a very special type of paper. This is called the goldenrod paper. So it's a goldenrod in nature. It is a indicator type of paper. Okay, so it indicates when we have some sort of base. So let's see what happens when we add in some Windex here. So let's take a guess. What do you think is going to happen? I have a goldenrod type color, the orange color, and I add some blue to it. What do you think is going to happen? So let's go ahead and let's pull again.
So blue plus this goldenrod color. Okay, let's see what you guys think. Blue plus this golden color. All right, we got some red, we got some green, some purple, some pink, some black. So lots of different options here. So blue plus this gold color. So let's see what we get when we spray it on. Wow. Quite literally, it says wow. So looks like we get this red color. That's interesting. So we spray blue Windex with this golden yellow sheet of paper and we get this red color that happens. Okay, that's interesting. So we spray Windex on. So maybe what we can do is we can add some more acid to this. So we have some vinegar, which if you've seen is this colorless liquid. It looks just like water. And we can start drawing on this. So and underline this, make it more clear. We can maybe draw a happy face up here. What else can we draw? Maybe we can outline this wow a bit more, just to emphasize that. Oh, there we go. So goldenrod, when we add vinegar, we can actually get that original golden color back. Just like that. And we can use it to draw more things. Okay, so those are some different kinds of indicators, but it's cool and all, but you know, they just have one color or another. So what else we have here is we have, so here we have a graduated cylinder. Inside we just have some regular tap water. Again, nothing too special about that. But this time we have another indicator. So something called universal indicator.
All right. So universal indicator, what does it look like to you? Let's make some observations before we start. So it's just like the water we have back there. It looks like it's a liquid, right? We can see that if I move the bottle around, it squishes. There's a liquid inside. And what about the color? Well, this universal indicator kind of looks like it's a dark reddish kind of orangey color, right? Now, what do you think will happen if I try to add this universal indicator into our water, right? So we're essentially adding a red liquid into a colorless liquid. Let's see if we can get a poll up and see if you can make a prediction for what will happen this time instead when we use universal indicator into water. All right, so looks like we've got some answers here. So let's see then what happens. So let me pour a little bit of this universal indicator into our water. Oh, here we go. Here's the rest of the poll. So let's make your predictions here and let's see what happens. So what has everyone picked here? What are your predictions here? All right, so it looks like some of you have picked yellow, some of you have picked green, some say orange or even black. Well, there's only one way to find out, and we can find out by testing it ourselves. So I will pour some universal indicator into our cylinder here. And take a look here. What do you notice? What is this color? It looks like it's green. Oh, very interesting. It looks like it's green. Now, earlier we talked about acids and bases, and we know that Windex is a type of base. So it's kind of like a soapy substance. So it's a type of base. Now, in the chemistry lab, we also have something that is stronger than Windex in terms of how basic it is. So we have a stronger base here. It's NaOH, or more commonly known as sodium hydroxide. And sodium hydroxide is considered a very strong base. Now, sodium hydroxide, when we add this in, it might create something different as well. And so let's see what happens. So sodium hydroxide is a liquid, right? It's a colorless and clear liquid. You can see right through it. See my fingers back there. And let's see what happens when we add sodium hydroxide, so a stronger base this time, to our flask or cylinder.
Oh, okay. I didn't expect that. So it looks like, what do we get? We get a purple liquid now.
Purple. I do like the color of purple. Is that your favorite color, William?
No, I kind of like that green more. Can we go back to that green?
We might be able to. So what was it that's opposite of a base again? Acid?
It's an acid.
Right. And what was James doing earlier with the straw?
He was blowing some carbon dioxide.
Right. So carbon dioxide is a type of gas, right? And so, but James looks like he's a little bit tired right now. I don't think he has any more energy to blow any more bubbles. But how can we get carbon dioxide? Is there carbon dioxide in a different form?
So let's see. We have carbon dioxide gas that we breathe out.
Right.
What other states of matter do we have?
Liquids.
Liquid.
Right?
I don't think we have any liquid carbon dioxide. What about solid?
Right. What about this thing here? This thing looks interesting.
What's that? Is that ice?
It looks like it's ice, but if I try to rub it on myself, it doesn't look like it's wet at all. What do you think this is called?
Well, it looks pretty dry to me because there's no liquid.
Right. So I think this might actually be dried ice or dry ice. Right. So dry ice, what is dry ice? Well, dry ice is actually carbon dioxide, but in solid form. And this carbon dioxide, this dry ice is actually really cold. It is -78 degrees Celsius.
Oh, that's really cold. I don't think you want to touch that.
No, I don't want to touch this with my bare hands. So that's why I'm using these tongs here. You can kind of see that it's starting to frost up the tongs. But similar to what we saw James do earlier by blowing bubbles, maybe we can use this dry ice, the solid carbon dioxide, to make bubbles instead.
Okay, I mean, that sounds like it'll make things a lot easier for us.
Yeah, it uses a lot less energy. All right, so let me just put this dry ice into the flask, into here.
All right, let's see what's happening. Oh, we got a lot of bubbles going on.
Look at all that smokiness. Now, looks like it's purple, and our goal is to try to go back to that green.
Yeah, I really want that green. Oh, it looks like, what is this, blue?
What is that color?
Oh, there's that green. Oh, I really like
Oh.
green. Okay, I'm pretty happy about that.
Oh no, it changed to a different color. Wait, What happened
yellow
here?
now.
Maybe we can go back to that green again. Maybe let's see. I'll
Yeah.
add some more sodium hydroxide again. Maybe we can change it all the way back. Let's see here.
Oh, there's that purple again. We have some blue, gray. Oh, there's that green I like. Yeah, let's keep it here.
It might be hard to just keep it there because look at it. It just turned yellow all by itself.
Okay, so it seems like these indicators are pretty cool. So indicators essentially tell us that whether or not something is acidic or basic. But what's so cool about universal indicator in particular is that it tells us how acidic or how basic something is. It's not just a yes or no or just one color or another. We get this rainbow of colors. So if we add more sodium hydroxide, we're adding a base and it turns purple. And then slowly as we make carbonic acid from the carbon dioxide, it'll turn blue and then green. And then eventually we'll get that yellow.
Right. I like all that smoke up there. Can we do something fun with it?
Yeah, well, I have a glove here. Maybe we could. Let's see what happens when I stick a glove up here.
It's waving at us.
Hey guys.
Hope you're enjoying the show so far.
Okay, so what else we can do? Well, we can also maybe, let's see what else we have. Well, we know we're making an acid with the carbon dioxide, but maybe we can add other acids as well. So we have here some vinegar. So if we pour this in, we actually get this nice orange color. Okay, and then Calvin also has some Windex. So if he sprays in some Windex, we know that Windex has detergent, has soaps in it. So when we spray it in, we get these bubbles of carbon dioxide.
And if I try to pop them, that should release that carbon dioxide from those bubbles. Now those bubbles look kind of cool, but can we make a bigger bubble?
Yeah, these bubbles are kind of small, so
let's play with some bigger bubbles then. So here we have another dish. Okay.
And we just filled this dish with some water here. Nothing special, just plain good water. To this water, I can add in some dry ice. Right, and let's take a look at what happens when we add in the dry ice. So it's just similar to what we saw before. It creates a lot of smoke, right? So the bubbling is from that carbon dioxide turning from solid into the gas. And then all this smoke here, this smoke is actually water condensation. So it's actually so cold that the water vapor in the air is condensing. And so that's why we see this white smoke here. Now we can make a big bubble if we have some soap with some water. So if we make a soapy water and just put a paper towel on here as well.
Okay. So we're gonna try and capture all that gas that's coming out into a bubble.
So here we go. Let's see if this works. And hopefully that should grow into a big bubble.
Okay, so watch as we go here. Okay, notice that here we can kind of jiggle it up a little bit. So as you can see, we got a nice dome filled with gas, this carbon dioxide gas. So maybe we can leave this in the background here without bursting it. Let me just carefully move this towards the back here. We're gonna play around with some of this bubble. Okay, so in here I have another big kind of jar here that I'm gonna put some dry ice in here. Okay, so I'm gonna go ahead and put some dry ice. Okay, and it's connected to a little tubing on the other end. It just helps me form the bubble that I need. Okay, so I'm just gonna go ahead and add some dry ice here. So I want to make sure that it's kind of closed through the top. So all the gas that's inside comes out through my little tubing here. So just gonna wait for some gas to make its way through the tubing. Maybe if I add a little bit more dry ice here, might help a bit. So here we go. Okay. And notice here now, I got the gas coming out. So as you can see, right from my hand, you'll see some gas coming out. So let me just go ahead and put this towards my little bubble solution here. Okay. And I'm going to dip it inside here. You can see it bubbles and makes some nice solutions here. Let me try that again. Here we go. So we got some bubbles coming off. Okay. Calvin here is going to capture some of this. Hopefully I'll be able to play around with it. So a nice and big one here. I think I have one more coming out. So look at that. You can play around this bubble. Okay. Now these are special kind of cotton gloves. So, you know, here it actually is very nice for the bubbles. Okay. So you can actually play around with it. Usually if it's with your bare hands, if he tries to pass it over to me, that tends to break it apart. But we have these special gloves, okay, made out of cotton so that you can see that we're going to be able to capture and hold on and play around with this. Maybe we'll be able to juggle around here with two, maybe. There you go. Oh, it popped one. All right, so that's pretty cool. All right.
Okay, so we saw like some bubbles, but I mentioned that the bubbles are kind of small still. I want something that's bigger. Do we have something that's bigger, Calvin?
Maybe. What do you have in there?
Well, looks like we have a tub. I have inside this flask, we have some water, we have some dish soap. So just the same dish soap you use to wash your plates, dishes in the sink. And then we have something called potassium iodide. So in chemistry, when we do reactions, sometimes they happen very quickly, but a lot of the times they also happen very slowly. They take hours, they take days, they take weeks to do. So sometimes we like to make things go faster. So we add potassium iodide to help our reaction happen faster. So what we also have here is some hydrogen peroxide that we'll pour out. So hydrogen peroxide, you might have used at home. Comes in a brown bottle, might be like 3% or 4%. But here we have 50% hydrogen peroxide. So what we can do is we can do this reaction and generate oxygen gas and make lots of bubbles. So what I'm going to do is I'm going to mix this liquid that looks very similar to water with our soapy solution here. All right, let's move this back and let's see what it looks like. Okay, so I'll give myself a countdown from 3. So 3, 2, 1. Whoa. And we get lots of bubbles. So just like that, we have this colorless liquid and we mix it with this soap and potassium iodide and we get lots of bubbles that happen very, very, very quickly. And so what's so cool about this is that this reaction will actually produce oxygen gas. And if you guys were here in person, you might even be able to feel that there's a lot of heat that's generated from this. Okay. So what's the opposite of heat? Well, we have something that's cold. So earlier on, we saw dry ice. Calvin mentioned that dry ice is negative 78 degrees Celsius. But maybe we can get something that's even colder. So what do we have here that's colder?
Well, so remember, carbon dioxide is a gas that we find in our air, right? Now, there are also other gases in our air as well. Of course, we need the oxygen to breathe. And so oxygen is a type of gas that's in the air. We also have a nitrogen gas, and nitrogen gas is actually the majority of the gas in our air. Now, nitrogen gas, we usually can't really see it, right? Because it's a gas. But what I have in here instead is that liquid nitrogen. And liquid nitrogen is actually really cold. The temperature for liquid nitrogen is about negative 196 degrees Celsius. And so if I try to pour this liquid nitrogen into our big dewar or this big flask here, just take a watch what happens to this liquid here. Hard to describe what you're seeing, all right? So at first, it kind of looks like it's colorless and clear, similar to that of water. But you can see that it's also boiling, right? Now, boiling doesn't always need to happen when it's very hot. In this case, this liquid nitrogen is also boiling, but it's boiling at very cold at that negative 196 degrees Celsius. But over time, it just kind of settles down, and eventually it will look like it's just water by itself.
Alrighty, so right here, as you guys can see, it's just a little sheet of paper. So we're going to show you how cold this is. Okay, so this is a sheet of paper, and we're just going to put it inside slightly here. Okay, so super duper cold. Let's just dip it inside. Let's just take it back out. And let's see how cold this is. Oh, can't really quite grab it. There we go. Okay, so oopsies. Super cold. So cold. Okay. Now, what do you notice that's on here? Anybody see anything that happened? Okay, maybe I'll just leave it here for a side for a sec while we wait till it cools down here. Okay, so while that's kind of waiting, let's just try something else.
Now, liquid nitrogen is really cold, and we can try and play around with this liquid nitrogen and throw stuff in there. And let's see what kind of happens. Well, first of all, I have this rubber tube, right? You can see that it is very flexible. I can stretch it out. It's also very flexible in the case sense that I can tie knots into it, or I can also release the knots. But what will happen if I put this into liquid nitrogen? Well, it's so cold that it should probably just freeze. And so if I dunk this in here now, let's take a look here. We can see that it is boiling again, the liquid nitrogen, because that tube is a lot warmer as compared to the liquid nitrogen. And then if I try to pull this back out, pull this rubber tube back out, we can see that it has indeed turned into a solid. It's frozen solid. I'm trying to pull it, tug of war with William here. It doesn't really want to stretch anymore. But hopefully you'll like this joke. What I have here is a U-tube. I'm laughing at my own jokes, but hey, that's okay. Now, so we've seen what a solid would happen when we throw it in there, but what do I have here? William's kindly blown me a balloon here. It's a very squishy balloon, right? Inside is just regular air or William's breath. Hopefully it smells nice. But what will happen if I throw this balloon into liquid nitrogen? What do you guys think? Maybe we can do a poll for this one. Will you think the balloon, will it pop? Will it shrink, expand, or nothing will really happen? We saw earlier that rubber tube freezes, right? What will happen to the balloon instead? So take a couple seconds here and let's see what do you guys think? All right, so a lot of people think that it might pop or it might shrink and expand. Well, let's give it a try. Let's throw this into the liquid nitrogen and try and figure and use our observational skills and try to see what happens here. So it's in the liquid nitrogen there. And what do you see so far? I'm just gonna wiggle it a little bit, maybe push it down, help it out. What's happening to the balloon? Looks like the balloon is shrinking, right? Maybe if I push this down some more, I might eventually get a very tiny deflated balloon.
Oh, that balloon sounds crunchy.
Yeah, but what happened to all the air? What do you think? Is it still inside? Maybe if I take it out, maybe we can find out. Let's see here. We'll can hear how crunchy it is. And as this warms back up, the balloon reinflates by itself. Is this magic or what happened here? Well, the air inside got really cold, and just like penguins like to huddle together, all of that air inside wanted to huddle together, and so it didn't really want to move around, and so the balloon deflated. It never leaked out because we tied off the balloon, but in this case, as we warm it back up, it will reinflate by itself. Now we also have different other things that we can try and throw into this liquid nitrogen as well. Earlier, James was a little hungry and he ate a banana. So we can try and throw a banana peel into our liquid nitrogen and see what happens here.
I'm gonna put back my sheet of paper. I'm gonna try this again. So
Great. And so that crunchiness kind of reminds me of chips. And so maybe we can make some banana chips out of this. So if I try and take this banana peel out, and maybe if I smash it onto our bench top here, maybe I can make some chips. And look at that. And maybe some more chips. So usually banana peels wouldn't shatter like this, right? It's only because this is so cold, it's all frozen, that it's all shattering.
right, so we just have a regular banana here, right? This is not gonna shatter, right? Even if we smacked it, it's not gonna really shatter.
And just taking our piece of paper back out, and it may or may not work, but that's okay. That's science sometimes. Experiments doesn't always work, but maybe I'll just leave this in the background for now and maybe something will happen to it. All right. Now, we talked about the gases that's in the air. And so far we've looked at a nitrogen gas and carbon dioxide gas, but we haven't really talked too much about oxygen gas. Well, for oxygen gas, oxygen gas is really important, right? Because it's what we need to survive. But similarly, it is also what fire needs to survive as well. And so if we want to light a flame or to light a fire, fire actually needs oxygen for it to burn or for it to light up. And so what I have here, what I'm trying to prepare here is a candle. And so I'm just lighting up the candle. Now, in this normal atmosphere, in this room here, we have oxygen gas. So that's why we can see this flame here. But notice what happens when I try to put this fire into our tank. So let's see. Oh, the fire disappeared. Maybe we could try it again, right? Now, the reason for why the fire is extinguishing or the fire is disappearing is because all of that liquid nitrogen is still continuously boiling. So it's going from, or it's essentially kind of evaporating. So it's going from the liquid nitrogen to gas nitrogen. And so it's pushing away all of the oxygen that's usually available in our air. Right? We can see that a matchstick does that as well. But what do you think will happen if I try it with a sparkler instead? Okay, so I have here a sparkler. I'm just going to light this up. What are your predictions if I try to put a sparkler inside our tank of liquid nitrogen? We notice that flame regular candles do not continue on. So with a sparkler, maybe something different will happen. So let's take a look here. I'm going to dip this inside. So far, so good. It's still lit up. And what if I sink this all the way down? What you should be able to see is that the sparkler still continues to sparkle inside all of that nitrogen. So a sparkler will continue to sparkle even without any oxygen gas. And so it actually creates its own oxygen inside this sparkler. Now, on the same idea with candles, I'll just try to shift everything over a little bit here. Let's make it look a little neater. We have a candle here. And to this candle, I'm going to add in some water. And a little bit of food coloring. Just to make our water green. It kind of reminds me of St. Patrick's Day. Right. Now we talked about how fire needs oxygen. Now, what do you think will happen if I try to cover this flame up with a flask instead? Do you think the fire will survive? Will it continue to burn? Or will the fire dissipate? Right, so let's see here. Do you think it might change color? Will it disappear, burn up, or nothing? All right, let's see what your responses are here. So let's say the fire might disappear or it might burn up. Well, let's give this a try. So I'll flip this flask upside down and try to cover up the flame and watch carefully what will happen here. Well, the fire did indeed disappear, just like how you guys predicted. But notice that something else happened as well. The water that was originally in the bottom got sucked up. Now, it got sucked up because it's not exactly magic. It is kind of magical to see water to go up instead of falling down, like due to gravity. But in this case, that fire used up all of the oxygen, and so it removed all of the oxygen space and allow the water to be pushed up into the flask.
Great. So since we were playing around with a little bit of fire, we always want to make sure that we are safe around it. So, you know, if you ever play around with fire, we always want to make sure we have some safety gear on or around. And in this case, we have our own fire extinguisher. So I'm just gonna, you know, show you what we have here, just to show that we're all safe here. So notice here, we have a fire extinguisher. This is a very special fire extinguisher. It blows out carbon dioxide in here. Okay, so it's actually a pretty cool thing that you have. So William, if you don't mind just holding on to this for a quick sec. So again, I showed you that piece of paper. I'm going to try the opposite. So right here, you can kind of see that, you know, I wrote on this sheet of paper, and it's actually really cool that if I actually put it against it, maybe we'll put it up a little closer here for you guys. William, would you like to do the honors? So we're going to try and heat up the paper. Okay, so let's just see what happens as we heat the paper from behind. Okay. Something's happening. What's happening here?
You're erasing the writing?
I'm erasing the writing. It's gone. Right? So what I was hoping to try and reveal back, and apparently it wasn't cold enough, or it didn't allow for the time to kind of occur, is if I put it back under some sort of cold temperature for some time, that message will actually reappear. Okay? Now, this is the case with erasable pens. Okay, so we have what we call friction pens. Okay, and basically with the eraser, it causes that heat and it actually helps erase the message that we have. And if you actually cool it back down, you'll actually make it reappear. Now, I think we have time for one more little fun activity here. Here we have 3 cups available. Okay, so I'm gonna show you that we have 3 identical cups, no holes. Show you guys here. Okay, so we got 3 cups here. And what we're gonna do is I have some water here, quite a bit of water actually. Okay, and I'm gonna go ahead and pour some water into the first cup here. Okay, so as you can see, I'm pouring some water in there. Okay, so where is my water right now? Well, it's in this first cup here. Okay, this is on your left screen, I believe. Okay, so if I take this and I put it into the middle cup, as you can see, it's being transferred into my middle cup here. Okay, it's now in the middle. Now let's do it again one more time. So now I transfer this into my final cup here, into the right-hand side. Okay, now where is the water? Well, the water should obviously be on the far right now, right? So it's all in here, okay? So watch very carefully as we mix the cups around. So it goes from the right to the middle, from the middle to the left, and now the speed will slightly increase and become a little messier. Maybe William, you can help me with a little bit here. You want to grab that one? I'll grab this one. Let's grab this one. Let's put it there.
Where did it go?
Where is it going now? Where is it? Okay, so let's do a poll.
Is it on the left, middle, or on the right? Where is that water? Okay, let's see what you guys decided. So no one thought it was on the right? Oh, looks like most of you guys thought it was in the middle, and then some of you guys thought it was on the left. Okay, so let's see who's right then. So most of you guys said the middle one. So if I pour some of this out. Oh, I don't think it was in this one. You guys said left. So let's see if we can pour any of this out. Oh, there's nothing in the left one, so it must be in the right one then, right? So let's pour some of this one out. There's nothing in this one either. So where's the water? What happened to the water?
Maybe it's magic.
Is it magic? Or is it just science? So if we look at each of these cups, this one's empty, this one's empty. But this one actually looks like it has something inside of it. So if I put my hand in this and scoop it out, you'll be able to see that there isn't water anywhere, but instead we have this kind of jello, slimy looking thing.
So what we have here is what we call sodium polyacrylate. It is some material that you can find, or a compound that you can find in diapers. So it helps absorb that water, right? So in this case, we're absorbing a lot of water. Now there are different types of these, what we call polymers, okay? Now it looks kind of like that at the beginning. So it's just kind of a white kind of sandy powder. Now, what I have here is something different from the original stuff that's inside the cup. So let's watch what happens when I go ahead and pour some water in here. Watch very carefully. Look at that. We got some fresh powder, snow almost. Okay, this is my Insta snow. Look at it grow. Okay, so look at that. Fresh snow. Okay, so it absorbed all that water. Okay, and I can add more to it and it'll continue to kind of grow. Okay, but it'll kind of spill over obviously, but it's some Insta snow in seconds. Okay, now we got one last thing here actually that we forgot. Something to deal with light. Okay, so William has this all set up here on the side.
So you guys saw earlier about candles and burning. And if you think of burning a candle, it produces quite a bit of light, but sometimes we can burn other chemicals in science and they can actually produce a lot more light. So what we have here are some strips of magnesium metal, and we can burn it and we can actually get a lot of light. So I'll use a little, I'll burn some of this at the end, and you guys will actually be able to see how bright it gets. So it's not just like a regular candle anymore. They can actually burn very brightly, almost like as if someone had some kind of wand to do magic tricks with. So let's see that again. Again, I'll burn this, and you can see how much light is actually produced just from a little bit of magnesium metal. Okay.
Alrighty, everybody. That is all that we have prepared for today. So I want to thank everybody for attending our virtual workshop. We hope that you guys can attend our in-person Science Rendezvous next year. Okay, it will happen around the same time next year. Okay, so on May 13th, 2023, and we hope to see you guys all in person. Remember, if you guys have any feedback or questions, please email SFU Science Outreach at sfu.ca. Remember that we are part of the Science in Action outreach team. So if you guys are interested in seeing more science workshops, please let your teachers know. They can contact us at that email, and you can book a in-person workshop coming this September, or you guys can continue on with other virtual workshops that we have available.
Okay, thank you, everyone.